not sure which one it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm gonna like clip it on myself so you have a better idea of what's happening with the volume. Hello, hello, hello. 1, 2, 3. You got me? We're good? Okay. Do you know if there's going to be any kind of like issues with feedback with the two microphones? Do you think there's any chance of that? Was there before? Yeah? Okay. Okay, we're going to give something a try. Hello, hello, hello. Woo! I'm very, very sorry. It took a second to catch up. Oh, Jesus, it's really loud. Do you have control of the volume back there for this? Because it's like it's going very loud. I don't know. Okay, because I could like hold this like 15 feet away. Yeah. I don't know. How can you? How well can you guys hear me? Just talking like this? Good? Okay, I think we'll just do this because I think this microphone's going to blow us all away. So, for my other session though, I'm probably going to have to use it, so, I don't know.
But as far as I spoke earlier, that one has something to do with the sound system that we have in there.
Because I tend to project, so I wouldn't need it that much. Yeah, I'm just worried about if we end up filling a lot of seats for my bio one. This one's chemistry, and like I'm expecting a pretty high turnout, but I still think it'll be okay with the other group. Yeah, I might just like leave it on the table or something.
Yeah, make sure you have that one because that's the tree one.
Yeah, I'll just like leave it on until then. Yeah. I'll be using like, yeah, that only. Yeah. Yep, yep. Nah. Is this like attached on here? Okay. I'm gonna temporarily remove this and then I will re-adhere it. This is on me, not you, so it's fine. I'll take the fall. I'll re-stick it later. Man, the hat. I am so all about this hat right now. It is fantastic. Oh, I was just saying it's fantastic. I'm just gushing over your hat. Yeah, it's pretty awesome. Well, it's much appreciated. Ladies love the hat. Yeah. So did you guys save enough seats for everyone, or is everyone not showing up? Or who all are you saving spots for? Okay. She what? Excuses, excuses. Yeah. No. I think this will go pretty good for you guys. Because it's this review stuff, it's not too bad. Although we do have like a lot of questions. Like I put way too many questions, so we're gonna see how fast we can do this. Yeah, I know, and they're like all problem solving. It's gonna be fun, but that's okay. Huh? Chem 1A is happening right now. Are you like just waiting until bio? Are you also here for chemistry? Cumulative, also including Chem 1? Or Chem 1A? Okay. Well, hopefully this is helpful. I was wondering, because I was like, I feel like you're not in my chem group, but I was like, I'm sure you have some reason to be here. I do both. I do all things. I basically am just, I'm kind of like a one-gal band here. Do what? Yeah. So I'll be here if you'll be here. Yeah. That'll be fun. Can everyone see this well? Can you guys see this okay? Can anyone not see this? Okay. I'm gonna try something. So, I'm gonna see. Okay, I wonder. I'm experimenting with having the microphone away from me. I don't know if that's still too loud. I think it is. Well, I'm also trying to not. Like, I'm gonna get excited about things. Okay, maybe this? This is okay? Yeah? Okay. Okay. I think I'm actually gonna move it a little bit farther just in case. If I get too excited, I'm gonna start shouting. And then I'm gonna blow it all up. Okay. If you guys do not already have access to this review, it's on our Google site, so the one we always use. I put a copy on there just to make sure everyone could get to it because this other one has been having some issues, so. On the Google site we always use. It's the SI one. If you look up, yeah, start Google site. Yeah, it's on there. But yeah, I will also extend the option to you guys if at any point, or not at any point, if you want to get pictures of my work at the end, you're welcome to do so. So that's an option to you as well. But there's a lot of pages, so I don't know if you want to take up that much space on your phone. Huh? You gonna heckle my session? Got a heckler in here. Yeah. Yeah. Does it look good? Yeah? Okay, cool. I didn't think you were coming. You've made your dramatic arrival. We're all good. Okay. Okay. If I can get everyone's attention, please. Yeah, I think this will work, doing the microphone like this. If I can get your attention, you are here, hopefully in the right place. This is our final exam review for Chemistry 1A, Chem 2040. Hopefully you're in the right place. If you are enrolled in Chem 2045, this will cover the first half of your class. And if you're in Chem 1B, then apparently this is a good review for you. Also, I'm going to do like a little mini self-advertisement real quick and let you know that if you are enrolled in Biology 1, I will be holding a session for that 30 minutes after the end of this session. So if you want to join me for that, I'll be here. You could be here. It'll be fun. I also want to let you know about something else. This something is this survey that they have up here. Back in the day, they used to have us do paper surveys, and so everyone would get one of these little pieces of paper, and we'd ask you to let us know how you feel about study union, the sessions, this session in particular, all of that. But they're trying to save paper, and I'm on board with that. So please, if you would be willing, on your way out, scan one of these codes, and please do fill out this survey. It's really helpful to us. It's helpful, to keep study union rolling, so we appreciate that if you can do that. Okay? We have quite a few questions on this review. We've got 41 questions. So that's quite a pace that we're going to be operating on. So we're going to do our best to get through it all, but please let me know if you have questions. Any questions before we begin? All right, excellent. Let's get started. So the first one we've got, we're going to do some matching, okay? So, man, this is echoey. Okay, hold on. Ooh. Move it further away. Okay. So first off, we're going to start with some matching, okay? We're looking at a couple different things. So we have all these terms, and then we're going to see which ones they go with here, okay? So, a summary of many past observations that has not been disproven. What do we think for that? So, is it a law? Is it a theory? What are we thinking? Yeah? It's a law? Any other thoughts? Because it takes quite a bit to get to a law. Are we okay with that concept? All right, let's roll with that. Let's go ahead and put law here. Thank you. Okay. So we get a lot of times, we get into this discussion about the difference between a law and a theory. Do you guys remember the difference between a law and a theory? I know this is digging way back. Anyone? A law, remember, is going to describe what happens in the world, right? A theory explains why that thing happens, or it attempts to, okay? So if we're saying a summary of many past observations, can you guys think of a law that we work with in science? Law of conservation of mass, right? So we've observed over time that you can't just lose mass in a chemical reaction, right? So we've seen that over and over and over. It becomes a law after so many observations. Also, law of gravity, right? So we've seen these things, okay? Let's see. A set of procedures that are meant to determine if an idea about phenomena is correct. What do we think? Experiment, yeah. So that's you doing your little science fair project or whatever back in the day. Also, let me know if you guys are not able to see the screen at any point, or if you're not able to see what I'm doing. Okay, next one. A tentative explanation for an observation should be testable and falsifiable. What do we think? So, you guys are saying hypothesis. Now, how do we contrast a hypothesis with a theory? Are you saying hi to me, or are you trying to answer my question? Okay. Well, you're just saying hi. All right. Well, hi. How do we contrast a hypothesis and a theory? Anyone? Yeah? Okay, awesome. Yeah, so a hypothesis is kind of a short-term explanation, right? It's, I see something in the world, I think this is why it's happening, and I'm going to go test it with my experiment, as opposed to a theory, which is after testing many, many, many hypotheses, then we come up with an overall explanation of something. So theory is much bigger. We're going to go hypothesis here. Now, don't forget the testable and falsifiable. That's incredibly important here, okay? So you don't want to forget those things, because that's really the key to a good hypothesis. You have to be able to test it, right? And it has to be able to be disproven. If I have a hypothesis that ghosts are real, is that a good hypothesis? Can I test that? Can I disprove that? Right? Because you could say, oh, well, you can't prove that ghosts aren't real, therefore they must be real. That's not a good scientific process. That's kind of a counterexample. Okay? And then a well-studied and well-tested explanation for a scientific law. What do we think? This is kind of the counterbalance for the hypothesis. Yeah. Yeah, so this is going to be our theory. Excellent. Thank you. Okay. All right. You know what? I'm not really. All right. That's making me sad time. So I'm going to just talk to you, okay? You guys can still hear me? Yeah? Okay. Because I don't like the ringing, so I'm going to just talk to you. Okay. Which of the following is not true of a solid? You know solids. Okay. Does a solid have a definite shape or defined shape? Yeah. Does a solid have a defined volume? Yeah. Is a solid compressible? So you guys are saying not so much. I'm going to flag that. Does a solid have a fixed density? Yeah. So we're going to go with C. Everyone good on Y? Now you might think you can squish something that's solid, but it's going to expand elsewhere. Compressible means that you can actually take air out of it. You know what I'm saying? And you can't do that with a solid. Okay. Which kind of plays into the fixed density thing, right? Because if you could compress it, then you could change its density. So both of those are like inextricably tied there. Okay? Cool. Now we're talking about chemical changes. So we're going to see which of these are not a chemical change. A bike rusting in the sea air, is that chemical? Yeah, that's a chemical reaction. We're forming iron oxide, right? Wood burning in a campfire, is that a chemical change? Yes. Sugar melting to form caramel? Yeah. What about carbon dioxide being chilled and compressed to form dry ice? No. That is just a change of state, right? Keep in mind that physical changes are changes that can be undone. Chemical changes can't be undone, right? Can you unbake a cake? No, right? So that's the idea of a chemical change, all right? It's like a lot more permanent. Do you have a... Yeah, so this is kind of an interesting thing. We say sugar melts to form caramel, but it's not actually melting in the chemistry sense. So that choice is a little bit misleading, because normally when we say melting, that describes a physical change. But in this case, we're actually talking about sugar burning, because that's what happens. That's why it gets dark and has that change in flavor when we make the caramel. It's actually burning the sugar a little bit. So that's what's happening with that one. So you have to be real careful with some of these, but in general, melting, freezing, evaporating, all those kind of terms, those are physical, okay? Thank you for that. That was a good question. All right, so we're going to pick that one. Which of the following is not a rule concerning significant figures? I know you guys really missed them. I wanted to make sure we talked about them. They're your favorite. Okay, so are zeros within a number significant? Yes, they are. Are trailing zeros that specify a value significant? So I heard a little discontent, so I'm going to flag that. Do exact numbers have no significant figures? What do we know about exact numbers? Like an equivalency? What do we know about exact numbers? How many significant figures do they have? Infinite, thank you. I'm like trying to see if I can hear anything in here. All right. So what about saying zeros that serve as a placeholder are not significant? Is that true? Yes, no? Okay, so we have this kind of issue between B and D, okay? So for one, I'm going to go ahead and give you a test-taking strategy. If you're not sure about B and D, but you're really sure that C is wrong, then you can pick that as your answer and you can go on with your life. However, we need to understand this, okay? Trailing zeros that specify a value, that's like 42.00. .00. Does that .00? Yes. So they are going to be specifying our value, right? And then we talk about zeros that serve as a placeholder. Okay, so that's something like this. It doesn't mean that there's 4 significant digits here just because it's a big number, right? How many significant digits are in this one? There's 2, right? How many significant figures are in the one above? 4. So our answer is going to be C here. But the thing that I want you to try and keep in mind is that if you have zeros that don't seem to be actually changing the value of the number, right? So if you have zeros like after the decimal place, for instance, or if you had like 0.030, right? Is that zero significant? Yes. It's significant because it has to be there for a reason. If it's not there to tell us how big or small the number is, there has to be another reason. That reason is that it's a more precise measurement. You guys kind of get this idea? So it's a little bit backwards thinking, but you got to kind of keep it in that context, okay? So let's put this into practice. I just broke the thing. No, I don't think I did. Okay, which of the following has the most significant figures? So we're going to test each one. This first one, how many significant figures? So it's a very small number, right? Does the fact that it's a very small number mean it was more precisely measured? Just because it's small? No. Just because it's small doesn't mean it's more precise. All of these zeros out front don't count. This only has 2 significant figures. All right? Because again, it's just about the size of it. If you only have zeros to tell you that it's really big, or if you only have zeros to tell you that it's really small, those zeros don't mean anything. Those zeros don't mean that we accurately measured that. You get what I'm saying? That's the difference here that we got to look at. Okay? This next one, how many significant figures? 4. We're probably a little more confident with that one. All right? Also, any non-zero digits are going to be significant. Hopefully we remember that. Okay, this one, it's 125,000. How many? 3. Again, 125,000, the only way to have it be 125,000, or rather, yeah, the only way to have it be in the 100,000th place is to add those zeros, but those zeros don't mean anything, okay? Like let me show you something, okay? If I have like a measurement here, all right, and we have 1,000, okay? And then I have 2,000, all right? And then we measure this about here, okay? Let's determine what this number is going to be from our measurement. I'll close the bottom here. So we have some kind of mystery liquid in there, all right? Do you know that it's definitely more than 1,000? Yeah, it's above the 1,000 mark. Do you know that it's definitely below 2,000? Yeah. So we're going to go ahead and put a 1 for the first number in the measurement, right? This isn't like rocket science, okay? Do we know for sure what the next digit's going to be, what the 100th place will be? Do we? Do we have any way to precisely indicate where that next place will be? No. So we're going to have to make our best guess, okay? The way that measurements work is you go as precise as the measurement will allow, and then one guess, okay? So we get our one guess. What do you guys want to say? Whereabout do you think that is? Like 6 or 7? We'll go with 6? Okay, so we went with 6, all right? That's our guess. But it's not 16, right? What's the number? 1,600. These zeros are not significant. Only the zeros from our measurement are significant. Do you guys understand that? That's the idea, okay? And then this last one, how many significant figures? What are we? 5, yeah. We're going to take these 5. So our answer is D. What? The one before the decimal? What about it? No, because the whole reason for those first 3 zeros is just to show that it's a small number. You know what I'm saying? So it's just giving you the scope. It's not giving you a precision in measurement. That's the takeaway here. These do get a little bit tricky. And again, you know, when you're taking your final, you are the master of your own destiny. If significant figures make your skin crawl, then save those for the end because they're worth the same amount as every other question. You know what I'm saying? So choose wisely what you do. Okay. Now we're going to do some math. Okay. We're going to determine this answer to the correct number of significant figures. So now we need to remember how we do measurements, okay? And I'm going to need your guys' help doing this calculation. All right, so we are going to have these multiplied together, and then we're going to divide it by the subtraction of these. So if someone can give me the calculation for the top 2 multiplied. Yeah? Yeah, give me like a bunch of digits, like just for the top 2 multiplied, right? Just give me a bunch of digits. Okay, that'll work, thank you. Okay, and so then we're going to divide this by these 2 subtracted. So what'll that give us? 3, 4, 5? Thanks. Okay, so what we need to do here, here's the thing. We're not going to actually round until the end, okay? But we need to keep track of our significant figures along the way, because that's going to come into play. So when we're multiplying and dividing, what's the rule? You guys remember? It's the least number of significant figures, right? That's why we did significant figures. So this one has 4, and this one has 1, 2, 3, 6, right? So we're going to round it to 4 significant figures, right? But we're not actually rounding. We're just going to indicate it. So here's what we're going to do. We're going to go 1, 2, 3, 4. And that's where that one stops. Okay? Then for the subtraction, what's the rule? So it's the least number of decimal places, the least number of digits after the decimal place. Okay? So this one has 4 after the decimal place. This one has 2 after the decimal place. Okay, so which one are we going to go with? We're going to go with the 2, right? So we're going to go 1, 2. You guys see how I did that? But again, we're not actually rounding yet. We're just tracking where we would be rounding. And then, come on, you guys, give me the answer that we calculate here. Yeah. All right, I'm going to go ahead and just take that. Cool. Thank you. All right, so now we have this division problem, okay? We need to look at how those significant figures are going to work. Again, if we are dividing, what's the rule? It's the least number of significant figures, right? So this one has 2 significant figures. Again, you got to look at where we said we were rounding. This one has 4. Everyone on board? So, what are we going to round this one to? 2, right? We're going to round it to this place. So what is our rounded answer? That's it. That's how we do it. So that's about as complicated as they get, but this is just to show you how the rounding rules work. Basically, the more calculations you do, the less precise you inherently become. Okay? We good? Let's move on. Okay. Which of the following is the highest temperature? You guys remember how to do this, right? We're going to convert all of them to something. You want to probably go to like Celsius? Does that seem okay? Yeah? So how do I convert Fahrenheit to Celsius? You guys remember? Huh? So you said 5/9. 5/9 multiplied by Fahrenheit plus 32? Minus 32. Minus 32 equals Celsius. Does that seem correct? Yeah? Yes. This? Fahrenheit and 32 are in parentheses. Okay, so you're saying 5/9 Fahrenheit minus 32? Yeah, that looks pretty good. So let's go with that. So what do we get for the top one, for the 20? So we're getting negative what? 6.6, okay. So this one is going to be negative 6.6, okay? And then the second one is in Celsius. How do we go from Kelvin to Celsius? So it'll be Kelvin minus 273? Yeah? Okay. So we're going to do our Kelvin minus 273 to give us Celsius. So what does this become? Yeah, it should be negative 173. Did we do that right? Okay. So what is our answer then? Our answer is B. Alrighty. Good stuff, good stuff. Okay. If the mass of an object is 3 kilograms and its volume is 10 milliliters, what is its density? What's our density equation? So we have density is grams per milliliter, or sometimes it's grams per centimeter cubed. It's mass over volume, right? Okay, so do we have the tools to be able to accomplish this? I think we can do this. We just need to deal with that, right? So we got 3.0 kilograms times what? What are we going to put on top? So we're going to put 1,000 grams over 1 kilogram. 3,000 grams. And it's highly possible that you can already do this in your head, and that's fine, but I'm just kind of showing this to you. Okay, and then we're going to do what after that? We're going to divide by the 10 milliliters, so what do we get? Well, we get 300, right? 300 grams per milliliter. That's it. Now, hopefully by this point, this is pretty simple to you. But again, keep in mind that with this final being cumulative, it's going to be important to not lose sight of these things. There's the simple stuff, you know? If a question seems too easy, it might just be because you're used to doing harder stuff. So it's not always that it's necessarily wrong. I mean, it could be, but it might not be. You know what I'm saying? Okay. We have a drug that's going to make people better at chemistry. Yay. This drug contains 10 milligrams per milliliter of the active ingredient, and the recommended dose is 20 milligrams per kilogram. So we want to know how many milliliters should a 120-pound person take in order to get an A in this class. We assume A being like, you know, the full effect. So how do we do this? We're going to set up our train tracks, right? We did this in SI all the time. If that means nothing to you, then we're basically going to do lots of conversion factors. So we'll start with our 120 pounds. But why am I starting with that? Yeah, because that's the thing that we need to convert, right? We're starting with that person, and then we're going to figure out what's our goal. How many milliliters, right? So we're trying to go from pounds to milliliters, and you might be thinking, I have no idea how to do that, and that's okay. All you need to do is to be able to get rid of the units that you're currently in and hopefully try and move forward. You don't have to have a total game plan for where you're going, okay? So I'm going to make my giant line. So we have pounds. We need to get rid of pounds. What could we go to? Could go to kilograms, right? So this is not on here. This would probably be given to you, but I'm going to give you that 2.2 pounds approximately equals 1 kilogram. I think that's about the conversion. We're going to go with that anyway because the concept holds true. So where am I going to put my pounds? On the bottom, right? Because we got to get these things to cancel. I know you might be thinking, I made it all the way to the end of this class. How dare you ask me to actually check my units? But that's really, really important, so please do that. Always cancel your units. It's so important. So now we're in kilograms. What can we take kilograms to? Milligram. Look, kilogram, milligram. That's there. Okay, so let's do that. Let's do 20 milligrams over 1 kilogram. Why did I put kilograms on the bottom? So we want that to cancel. Cancel, cancel. Now we're in milligrams. What can I convert that to? Milliliters. 10 milligrams per milliliter. Okay. So now our milligrams goes away. We're in milliliters. Where do we go from here? That's where we want to be, right? That's the goal. So that's good. So we found our way. So Slowly but surely. So what do we get? Yeah? 109.09. Is that what everyone got? Did you get something like that? Here? Because we had 20 milligrams per kilogram. So you're saying instead of 10? Well, because we have this conversion, that's the only way that we can get out of kilograms. You know what I'm saying? So it's a weird thing because you're thinking milligram, kilogram, like we could have converted that differently, but it's more of like a medical thing. Like when they do dosage, that's how they prescribe it. So we have to go with their conversion. Yeah. I get what you're saying, though. Thank you for that. Okay, so we have this answer. It's in milliliters. What should our sig figs be? We might as well check this. What did we start with? We started with our 120, which is how many sig figs? 2, yeah. So we have 2 of them, so we got to round this. What's it going to go to? 110. Okay, yeah. You didn't get that as your answer? Doing this calculation? Can we check it real quick? Did you calculate across the top, across the bottom, and divide? Everyone else got 109? Okay. Maybe if you want to see me at the end, we can take a look at how you're using your calculator. That might come into play here. Because it looks like everyone else got that answer. Do what? Okay. You also got 109? Okay, so we're going to go ahead and go with this answer, but you can come talk to me at the end. We can try and see what's happening with that. It might be something with your calculator. I'm not totally sure. Okay, let's move on. So we have 8 grams of calcium in a 20-gram sample of calcite. Now, given the fact that we're very used to like making chemical reactions, you might be thinking, I don't know what calcite is, but just hold on, because maybe we don't need to know. All right, so then we're asking how much calcite must be obtained in order to collect 30 grams of calcium. How do you want to do this? Huh? Start with the 30? Okay, so we know that we have this. There's kind of 2 ways that you can do this, but I'm going to take it that way because I like doing that. But either way will work. So we have this 30 grams of calcium. We want to know how much calcite. I'm going to go ahead and say in grams. I didn't mention that earlier, but that's what I intended by this question. Okay, so do we have any conversion factors then that we can use? Yeah. The grams of calcium, and then what? Yeah, so we can say that we have 8 grams of calcium equals 20 grams of calcite. Okay, so we can treat this as a normal conversion factor kind of problem. We could do 30 grams of calcium times, and we can just do it the way we would normally do it. We're trying to get rid of grams of calcium, so we're going to put that on the bottom, right? 8 grams calcium, and then 20 grams calcite, and then have those cancel. What do we get? 75? Cool. There is another way, equally useful, yeah? You know, I'm not totally, have you guys been given that before? I assume you'll be given conversions that aren't just between units. You know what I'm saying? Like standards, like if you had to do like feet in a mile or something, like I don't think you're gonna just have to like know random standards offhand. Yeah. But I'm not totally sure, so I can't say 100%, but unless you were told, make sure you remember this, then I can't imagine it's very likely. But yeah, so the other way that we could do this, if you're curious, is we could make it like proportions. So you could say like 8 grams. I'm going to just call them A and B because I'm getting really tired of writing them out, okay? So we have 8 grams of A per 20 grams of B. And then we have, 30 grams of A over X, and you could cross multiply and then divide. So that's just another like approach to it. My preference personally is doing the conversion factor because it's not like you don't need to know how to do those. You know what I'm saying? But technically the logic will work either way. Okay? Good stuff. Okay. So our next one, which of the following statements is inconsistent with Dalton's atomic theory? Yeah. Yeah, so I didn't actually round that one to sig figs, but yeah. On a test, I don't know to what extent you'll actually be grilled on sig figs other than when they ask about them. You know what I'm saying? Like, I don't think, again, I can't tell you for sure, but I don't think that you would have like 2 answer choices that were basically the same but rounded differently because they're more concerned in making sure you know the other concepts. You know? On free response, I can't say for sure. Free response, I would say check all your sig figs. Yeah, I was speaking more in terms of multiple choice, but yeah, if you do have free response, I would be real careful. So probably at the end, just do like a sig fig check through your exam. You know what I'm saying? Because you never know if they're going to knock you or not for that. I can't imagine it'd be full credit off, but you might lose a couple points. So that'd be something to think about. But again, if your exam is multiple choice, that's kind of what I was getting at is I don't think you would have to deal too much with sig figs beyond when they're actually asking you about it. Okay? All right, so which of the following statements is inconsistent with Dalton's atomic theory? I know you guys spend all your free time thinking about Dalton, so this should be easy. Wood burns by combining with air, and then the products are a rearrangement of the reactants. Does that seem pretty consistent? Yeah? So it's the idea that we can't do alchemy, right? Remember we talked about that? Like, you know, when they tried to make various things into gold, like, unless it already has the components for it at the start, you're not going to be able to make it at the end. So that seems pretty consistent. And again, we're asking inconsistent. 2 isotopes of carbon exist in nature, one weighing 12 AMU and one at 14 AMU. Does that seem consistent? Yes, no, maybe? We're not sure. We don't remember Dalton. I'm gonna put a little line here. We'll think about that one in a second. Methane is a gas composed of molecules that each have 1 carbon and 4 hydrogen atoms. Does that seem pretty good? Remember that was the whole, like, the definite proportions? We talked about that. Based on mass ratios, it can be determined that carbon dioxide has twice the amount of oxygen per molecule as carbon monoxide. Does that sound pretty good? What was that principle? Do you remember? That was multiple proportions, right? Remember we talked about that a little bit conceptually? So this one, I deliberately gave you guys kind of a tricky question here. choice B is not incorrect in terms of the modern day scientific community, but it is inconsistent with Dalton's atomic theory in that he said something to the effect of all atoms of a certain type will have all the same properties, and these two atoms have different weight. So Dalton did not account for isotopes. He also didn't account for ions. You guys see kind of what's happening here? So we had a little bit more of a simplistic view of the world. So this one is going to be our choice. Yeah? Yeah, I think that's reasonable. Yeah. Okay, cool. Let's keep going. All right, which of the following scientific conclusions is not true? Okay, so again, I know we have more scientists. I'm sorry about this. Thomson discovered negatively charged particles called electrons. Is that true? That was true. Rutherford's gold foil experiment showed that atoms are entirely empty space. That'd be kind of weird if atoms were entirely empty space, because then, you know, like we're made up of atoms, and then we have sort of this like esoteric, like what is life situation. I don't know if we want to embrace that on this Sunday. Let's look at the rest of the choices. Curie discovered elements that have that constantly emit particles, a process known as radioactivity. That was good, right? Yeah. Her life was very sad. You don't want to be the person that discovers radioactive stuff. John Dalton considered atoms to be small, dense balls. Was that true? So we're not asking, to be clear, we're not asking, is the concept true? We're saying, are those words consistent with what they thought? In that sense, yeah, that was his scientific conclusion. For B, that's going to go ahead and be our answer here. He concluded that atoms were mostly empty space, right? Remember, because it was talking about how, like, the electrons, like, went through the foil, but some of them bounced back. It was that whole thing. Maybe you remember, maybe you don't. But anyway, that was the difference. Okay, it was that he said they were mostly empty space, so it's a very small distinction. Okay. Now we got diatomic elements. I know there's a bunch of different ways to remember them. There's the one, something about beer, but that's kind of weird to me because this is a freshman level class. So I have a different one. It's not even really it's just a weird thing. So it's called Brinkelhoff. I don't know if you've heard of this, but it's all of them. Brinkelhoff. And for some reason, I will remember Brinkelhoff until the day I die. I don't know quite what it means, but it's a word that you can say, and it has all of the elements that are diatomic. What does it mean to be a diatomic element? Yeah, so it's always going to be like Br2, N2, right? So what's our answer going to be then? So bromine is one of them, chlorine's one of them, nitrogen's one of them. Is carbon one of them? No. Get out of here, carbon. You're in all our other problems. But yeah. Diatomic elements. Don't forget these weirdo little things. Okay. Which of the following statements about atoms is not true? Okay, so does changing the number of protons change the charge? Now, I know you're probably thinking about other implications here, but what do we know about protons? Yeah, so they have positive charge, and then they also, do they have mass or do they not have mass? They have mass. Okay? What about electrons? Do they have a charge? Negative charge, yeah, excellent. Negative charge. No mass. Not to be confused with no mass. All right. Was that for me? No? All right. I wasn't sure. There's like a little bug flying around here trying to attack me. Neutrons, do they have a charge? No charge. Because neutron, like neutral. Do they have mass? Yeah. Now, as you might recall, this is slightly misleading. Electrons do have mass, but their mass is approximately 1/1000th the mass of a proton or a neutron. So the entirety of the scientific community sat around one day and they were just like, they're so small, we're just going to not count them. So that's just that. So, you know, if you're curious how that went. Lots of calls get made without our vote. It's not a very democratic scientific process. Okay, but we have these questions. If we change the number of protons, do you think that'll change the charge? Yeah. Does changing the number of electrons change the charge? Does changing the number of neutrons change the mass? So we actually have an all of the above, finally. However, what is so special about changing the number of protons that we might want to know about? Yeah, so I think a lot of you guys are telling me here, it changes the actual element that we have, right? So your proton is like, if everything else changes, your protons are going to stay consistent. Once you change your protons, you have something totally different, okay? So keep that in mind. That's like that's our rock here. We need that to stay solid. Otherwise, we're not going to know what's going on. What do you call something that has a different number of electrons than a neutral atom? What do you call something with a different number of electrons than a neutral atom? An ion, right? Ah, we remember this. We're taking it back. All right? What do you call an atom with a different number of neutrons than a normal atom or than another atom? That's an isotope, right? Ion, isotope, ion, isotope. What's a positively charged ion? It's a cation. I'm going to make a fool of myself for one last hurrah. Cats have paws. Therefore, cations are positive. Right? Ah, I got you. All right. So that's no shame. You just have no shame standing up here doing this. It's fine. So you'll remember that, though. Okay? Let's do some application. How many electrons are found in Cl minus? I apologize that it's really difficult to see, but this is Cl with a giant minus. But when I typed it out, it was a very, very little minus because it was a superscript. Okay, so here's what we need to do. This is basically how we're going to operate, okay? We know that chlorine has how many protons? 17? How do you know that? Yeah, it's number 17 on the periodic table. So the proton number is the atomic number. That's also an important thing. What does your mass number represent, out of curiosity? Yeah, so it's protons plus neutrons, right? Because they both have mass, so that makes sense. So if you already know the number of protons, you can probably calculate neutrons based on the mass. So I'm doing all this really quickly because I'm assuming that by just mentioning it, you guys will hopefully remember. Okay, but stop me if I'm like going too quick. Okay, so we know we have 17 protons, all right? But we have this minus sign, right? Because in a normal situation, in normal chlorine, we want 17 protons. How many electrons does that mean that we would have normally? 17, why? Yeah, so we have, I almost treat it like a math problem, right? So we have plus 17, minus 17. We have 0 net charge, right? Right? But for Cl minus, we're going to have our protons is still plus 17. Why? Because it's still chlorine. I'm going to keep just making sure you remember that. Okay? And then we need to find the electrons. What do we need the overall charge to be? -1. So with that in mind, what does the number of electrons have to be? 18. That for me, like for me personally, is the best way to not get confused with, is it one more or one less? Because it just turns into this whole thing. Because you think negative, why is there more? And it's complicated. But find whatever way works for you. Just find a system that's consistent, that you can be like, okay, despite the fact that I'm on this final and I might be a little bit nervous, I know what I'm doing. This is my process. I'm going to get these problems done and walk out this door champ. Okay? That's what you got to do. Let's keep going. Okay. What is the primary difference between carbon-12 and carbon-14? First off, before we answer it, what do we call things like carbon-12 and carbon-14? Yeah, we just talked about this. They're isotopes. Okay? So carbon-12, let's take a look at this. So carbon normally has how many protons? 6 protons. And then what does the 12 represent? Yeah, that's the mass of it, okay? So this might be how you'd see it on a periodic table. Here's a tip, because you never know how your periodic table is going to look, whether you're taking a standardized exam or whatever the case may be at any point in your life. Which is always going to have to be bigger, the atomic number or the mass number? The mass number, right? Because the mass number is protons and neutrons, but the atomic number is just protons. So that's a way you can always, no matter where they put it around the element. Okay? So, how many... Okay, so for this one, we're going to say our protons are what? For carbon-12. 6? How many electrons? 6, right? We don't have any reason to believe that there's a charge, so it's 6. How many neutrons? How do you figure that out? So we'll do 12 minus 6, right? Because that's protons and neutrons. That's just protons, so you think, okay, we do a subtraction here. 6. Okay, let's do carbon-14. How many protons? You sure about that? You don't want to do 8? Why is it 6? Because it's carbon. Ugh, carbon. Okay. How many electrons? I'm going crazy, guys. 6. How many neutrons? 8. So what's my answer? Good stuff. Okay. Element X. Don't you love these when they don't give you any context clues, so you just have to go purely based on the concept? Element X has 2 known isotopes, X25 and X28. X25 has a 62.4% abundance in the environment, and so we want to know, what is the atomic mass of element X? What kind of problem is this? This is an isotope abundance problem. How do we do it? We need to figure out, it's kind of like, okay, I'm gonna take you back into the day when I started college. We didn't have, I'm gonna sound like I'm 90. We didn't have all the stuff on like web courses where it calculates your average perfectly. You just had like this thing, this is your score, this thing, this is your score. So if I got 100 on a quiz, and if I got 100 on an exam, those were not averaged equally into my grade. You know what I'm saying? Or if I got like an 80 on each, that wasn't averaged equally into my final grade, okay? Because let's say the quizzes are maybe like 20% of your grade and the exams are like 80% of your grade, right? So my exam score is worth more overall than my quiz score, you know what I'm saying? So you actually had to go in and do this calculation for your grades, unless you just wanted to wait and find out. what came on your transcript. So we're going to do that, okay? So we are going to take x25 times our abundance, okay? So we'll do times 0.624. Okay, so the other thing too that I didn't mention here is our 25 and our 28, those are going to be our masses, right? So I'll actually go ahead and get rid of the x just so it's a little bit less confusing. But we're taking this mass, which is 25. So here's what we're saying here is that this one isotope is going to occupy 62% of the entirety of that element in the entire world. Okay? So if we want the average of all of the weights of them, we have to give that one a 60% share, right? It's a little bit more than half, okay? And then we're going to combine that with the one that's 28, and then what are we going to multiply it by? Because we don't have the percentage of the other one. Huh? 23 what? 0.376. How'd you get all that? Okay, so it should be, what's 100 minus this? 37.6? So hold on, I'm messing up my numbers. 0.376. You see how we did that? Because it said that there's two isotopes, right? So you know that they have to add up to 100%. That's how that works. So go ahead and do this whole thing for me and tell me what you get. Yeah? What was it? 55.71? 26.128? Okay. So yeah, I don't know if something happened with your numbers there for a second. But yeah, so, okay, let's think about this though, right? Another thing that I want you guys to think about as you go into your final, hopefully you've been thinking this throughout your exams, is does my answer make logical sense? Because you calculate something and you're like, well, that's a number. That's fine, I guess. But no, I want you to put context to your numbers, okay? If the only two isotopes are 25 and 28, should we have an average of more than 28? Should we have an average of less than 25? So you have a range, right? So if it's 26.128, is it closer to 25 or closer to 28? It's a little bit closer to 25, right? Does that seem consistent with what we were trying to do? So does this answer look correct? You see how we do this? This is kind of how we want to approach. All right? Okay, now we're calculating for atoms. Get back to our old pal. My boyfriend calls him avocado. It's Avogadro. Avogadro's number, right? Okay, anytime we talk about atoms or if we talk about molecules, we're almost definitely going to need Avogadro's number. So, let's take a look at this. We have a 2 kilogram sample of lead. Now, what can we do with this? Yeah? Okay, yeah, so let's convert it to grams, right? We're going to put our kilograms on the bottom. Kilogram, 1,000 grams. Kilograms go away. Okay, what do we need to get it into now? Yeah? Convert it to moles. Do we have a way to convert between grams and moles? I feel like we do. Talk to me. How do we do it? We got any periodic tables around? Maybe, maybe. All right, give me some digits. Tell me what's happening. What? 207.2? All right. So, we are saying that we have 207.2. I'm getting ahead of myself here. That's a 2 grams of lead in 1 mole of lead. You see why I put the grams on the bottom? Because grams have to go away. And now we are in moles of lead. Pretty much when in doubt, go to moles. Once you're in mole land, there's many opportunities for your life. All right, what can we do with these moles? Huh? Moles to atoms? Atoms to moles? Do we have a conversion? So we have 6.022 times 10 to the 23rd power atoms of lead in 1 mole of it. And that's where we're trying to go. So now we need an answer. It's probably going to be big. Yeah. Never mind? Okay. All right, everyone get some like 5.8 around there? Yeah? Okay. You said 5.812? 813 times 10 to the 24? So let's do our check. And again, I'm being very, very bad with my sig figs here. What should we actually round this to for sig figs? 6, right? So this will actually be 6 times 10 to the 24th. But in any case, let's do an analysis. Does this number make sense? How big are atoms? Like, in a qualitative sense? Very small, right? Can you just be like, wow, your atoms are looking ravishing today? Like, probably not. That's a little strange. So you can't actually see atoms with your naked eye. You can't actually see atoms in a microscope. So it's very difficult. They're very, very, very small, right? It's like the smallest single unit pretty much that we work with. So does it make sense that if you have 2 kilograms of something, that's like almost 5 pounds, does it make sense that you'd have a lot of atoms? Yeah, so we're expecting a big number. Anytime you have atoms or molecules, expect a big number. If you don't have a big number, you've got a problem. And if you start with atoms or molecules with that big number, and then you're converting to like moles or grams or something, and you still have like a 23rd power, there's probably an issue. So just kind of keep that in mind as you calculate these. All right? But don't forget that Avogadro's number is only valid converting with moles. You can't do it with grams or anything else. Okay? All right. Let's do the next one. Oh man, you guys are so excited for naming. I'm going to name the heck out of these things. All right. We want the formula for magnesium chloride. My first question is, what kind of compound is this? I said my first question. You're just like, I'm already there. Is this an ionic or a molecular compound? Ionic, how do you know? Metal and non-metal, okay? So we're going to go under the ionic system of naming, okay? Which means that we're going to go ahead and take the charges for each of them that we would form on the periodic table, and we're going to do something with it. So for magnesium, what charge do we form? 2, right? How do you know? It's in that second column on the periodic table, right? You guys remember that? Okay. Mg2 plus. And then we have chlorine. What kind of charge? So it makes a minus, right? That's one of the halogens. So there's two different ways to think about putting these together. One of them is simply swap and drop. And when you take the numbers without the charge and you put them as the subscript for the other one. So you would have Mg1Cl2, or more simply, MgCl2. That's one way to think about it, so we already have our answer. The other way to think about this is to actually think about proportions, right? So we're trying to make something neutral. That makes sense? So if we have this magnesium and it's got a positive 2 charge, if we only put it with one chlorine that's got a negative 1 charge, what's our overall charge? You guys hear me? We got a positive 2 from magnesium. We got a negative 1 from chlorine. If we put one of each of them together, what charge do we get? We get a positive 1, right? That's not good enough. We need it to be 0. Let me kind of just write this. So we have the Mg is giving us this positive 2, right? Chlorine is giving us this negative 1. If we do 1 and 1, that's not going to neutralize the positive charge. We need another chlorine. We need another negative to neutralize that positive. If that confuses you, swap and drop is your best friend. Make sure after you do the swapping and dropping that you have it at its simplest ratio. Okay? Because that's how ionic compounds roll. Okay. So we have iron 2 oxide. What's with the numbers? So iron is what kind of thing? Iron is a transition metal. That means that it can take on different charges depending on, how it's feeling that day, and other factors. So this 2 represents what? Yeah? Well, it actually represents the charge represented by the iron, right? Because that's what changes with iron. So we're going to have Fe2 plus. Now, if it had a 1 in parentheses, it would be plus 1 instead of plus 2. Okay? But that's the charge on the iron. Okay? And then we have oxygen. What charge does oxygen get? Minus 2, 2 minus. Okay? So again, we have our 2 options here, but you just got to be consistent with the process. If we do swap and drop, what do we get? We should get Fe2O2. But is that the simplest whole number ratio? What's the simplest ratio? FeO. You're like right there with answering these questions. I'm just trying to make sure everyone gets what's happening though. So the other way to think about it is if you've got a positive 2 and a negative 2, if you put them together 1 and 1, then it's already neutralized, right? So you only need one of each. Either way will work, but just make sure you reduce it if you're doing the swap and drop. Okay? So now we're going to name, yes, ma'am. That's a very good question. Our question was talking about empirical formula versus molecular formula. That would have to be stated to you. But both empirical and molecular formulas are part of covalently bonded compounds. We're talking about ionic compounds. Yeah, so in the case of ionic, it's always going to be the lowest ratio. But if we're talking about empirical or molecular, you would be told in the question what you're looking for. Yeah? Yeah, so that's a very good question. Why in the naming it's not magnesium dichloride? The only time you're ever going to use prefixes is if you're in a molecular compound. So given that this is an ionic compound, you simply name the first thing, magnesium, And then you name the second thing, but instead of chlorine, you put IDE at the end. Yeah. So no prefixes in these parts. Okay? So we're going to name this one here. We have KNO3. Okay, so is this ionic or molecular? Oh, yeah, do you have a... Like, can you got to work with me here. I'm very happy that you're so confident in these, but I want to make sure everyone else is too. So we got to kind of get the hive mind ready. All right. So is this ionic or molecular? You sure about that? The K, is that a metal or a non-metal? Potassium is a metal. This is an ionic compound. Do not be fooled. You have a polyatomic anion, however, and that might be confusing you. But it's still ionic. Okay? So we're going to name it the same way that we were just talking about, right? We're going to name the first thing, which is potassium. So that's not really helpful to us. And then we have to name the second one. What do we call NO3? If we were going to do it the same way we would do this one, it would be nitride, right? But that's not correct here. If it was nitride, it would be K and then N. It's not just N, it's NO3. What is NO3 called? Nitrate. Which, as you're so kind to help me with, that's going to be our answer. You guys see how we do this? So make sure you review your polyatomics. I know some classes were asked to memorize them, some classes were not, but regardless, you should be looking at them. Okay? Because you still want to be familiar with what's happening. All right? Okay. Alrighty, so we want to name this compound. It's PCl2. Oh, I'm not, no. Wait, what? Okay, we've got ladybugs in here. All right, so this one, is it an ionic or a molecular compound? Do we have a metal in the house here? We have phosphorus and we have chlorine. They're both non-metals. This is molecular. Make sure that you review these things, okay? Whew. My voice is starting to go. It's not good. Okay. So, the rule for naming these is what? We're going to name the first one, okay? But we're going to do this a little bit differently. So, we're going to go phosphorus. And then how do we deal with that chlorine? Yeah? Yeah. Yeah, so you have to have a prefix here. So, what's the prefix for 2? Dichloride. Okay? A good way to remember this, I like to think about stuff that you probably already know, right? If I gave you NaCl, what is the name for NaCl? Sodium chloride. It's table salt. You've probably heard that before, right? So that's, like, I like to think about, like, stuff you already know and then connect it to the principle. That way you don't forget. So sodium chloride, you think about how that was named, right? And then we think about something like carbon dioxide, right? Carbon dioxide is CO2. So that's molecular. Dioxide. All right? All right, all right. So, we're going to ask, how many grams of oxygen are in 20 grams of carbon dioxide? We actually just got here. Okay? So, we need to think about how this works. So, we're going to start with 20 grams CO2. Okay. And then, when in doubt, what should we probably do? Convert to moles? Yeah. Let's go ahead and convert to moles. All right? So, in 1 mole of CO2, how many grams do we have? Anyone got it memorized yet? It's about 44. I'm kind of rounding here. And again, if you have a free response exam, make sure that your numbers are like really precise. But if you're doing multiple choice, just round everything, because it's not gonna, you're not gonna be docked for like 15.99 instead of 16 for oxygen. You know what I'm saying? So just keep that in mind. So now we're in moles of CO2. We are trying to get to oxygen. Do we have a way to do this? How many moles of oxygen are in a mole of carbon dioxide? This is a weird concept. We only dealt with it for a short time. But if you look at the CO2, because there's 2 oxygens here, we can say that there's 2 moles of oxygen in 1 mole of CO2. Which I know is a weird concept. You could also look at like water, right? There's like 2 moles of hydrogen in every mole of water. So things like that, just make sure that you're comfortable with doing that. Okay? And now we're in moles of oxygen. And I want to jump in before you ask me. Your question, hopefully, is why is it just O and not O2? Because we're not talking about oxygen as a freestanding element, like participating in a reaction. We're talking about oxygen, just the letter. Okay, so the diatomic isn't really going to apply here because we're not reacting with it. But what can we do? How do we find grams of oxygen? From moles of oxygen. Do we have a gram to mole conversion of some sort? Mayhaps. Yeah? So, 1 mole of oxygen is 16 grams. Please keep in mind that in almost every situation other than this, you'll be dealing with oxygen as a diatomic element as O2. And the grams per mole of O2 is not 16, it's 32. So don't lose sight of those things. Make sure you actually look at everything. Okay? And what do we get? Huh? 14 point what? 14.54? Thank you. I'm going to just write it out so it doesn't seem weird, okay? Okay, so we have an answer. If we were going to round it to sig figs, what would we do? It'd be what? 14.5? Yeah? Okay, so again, I want us to think about this in the context of logical understanding. So, does this answer make sense? Does it make sense that out of 20 grams of CO2, 14 of them might be oxygen in this case? Okay. What would be a weird answer? Like, what if you got 24? Would 24 be an okay answer to get? Probably not. So if you do some kind of mathematical voodoo on your exam and you get some weirdo answer like that, be aware, okay? And make the necessary corrections. Or just flag it and move on. If you realize that your answer is totally off base and it's taking too much time, come back to it. You've got time. Okay? So there's my thoughts. Okay. Now, this one is one we were talking about with the empirical and the molecular. So here's what we're going to do. We want the molecular formula for a compound containing 27.3% carbon and 72.7% oxygen. Okay? So here's how I'm going to treat this. We're going to take each of these, and here's what we could do. With them having proportions like this, you can actually treat them as gram amounts. Do you guys remember being able to do this? Because if it was 27.3% of 100 grams, then it would be 27.3 grams. Now, you can apply this to any amount, and I actually challenge you to do so when you're studying. You can apply this percentage to like 300 grams and just see what happens. As long as you apply both percentages, you'll get the right proportion, and it'll work out fine. So, something to think about here. But we're going to just take it straight to grams because that's an easy conversion. Okay? So we're going to do 27.3 grams of carbon. Okay? And we want to get this into moles. So how do I do that? How many grams? $1.279? 2.279. All right. Okay, so we have that, and that's all fine and dandy, but we think, like, what do we do with this? Well, we'll get there. So now we have this, 72.7 grams of oxygen. And again, we have this weird thing where I'm not putting it as a diatomic element. The only time that it's going to be diatomic is if it's actually in a reaction. We're just trying to analyze something, so that's different. But every time we do, like, something reacts with oxygen, if it's reacting with oxygen, it's in the environment, it's O2, okay? I just want to make sure I'm not, like, throwing anybody off with my weird oxygens here, okay? So 1 mole of oxygen is going to be equivalent to what? We just did this. Right? 16 grams. What do I get? 4.7 what? $4.5? Oh, sorry. Okay. 4.5. Is that it? All right, whatever. We'll take that. Okay, we're going to work with this. All right, so we have some numbers. Now we're going to set up a preliminary empirical formula, okay? And we're, like, definitely going to run out of space, but that's okay. So we're going to do carbon of something. So we're going to do 2.279, and then oxygen 4.5. Now, a couple things here. The reason I'm putting carbon first is not abundantly, like, necessary to your understanding for this class. It has to do with electronegativity, which is something you'll learn later. But if you look at your answer choices, you'll figure out what order they want you to go in. Okay, so it's not that big of a deal. But you can put them in any order as long as you have the proportions, because you'll still get the right answer. And the idea here is that these are the mole ratios of them to each other. So we just need the smallest whole number ratio, right? That's how we do this. So how do I find the smallest whole number ratio? Yeah, so we're going to divide by the smallest one. 2.2, I can't even read what I wrote, 79. And then this is going to be divided by 2.279. So in this case, carbon has what what subscript? It's got a 1, right? I'm going to write the 1. I know 1 is implied, but I'm going to write it just so we see. And then oxygen is going to have what? 2? Yeah, so in this case, you're going to round it to the nearest whole number because you'll probably get a whole number. The only time when it's not going to be a whole number, if you get something that's very, very close to like something that'd be 0.5. So for instance, if this was going to be like C1O1.5, then go with the 1.5, but then double them both to get a whole number. You know what I mean? So just work your numbers until you get a whole number. Okay? So this is our empirical formula. But that's not what we asked for. So I'm going to, okay. I'm going to take another sheet of paper because we ran out of space. And I'm going to write a little, I'm going to scribble a little bit on the bottom here. We're almost done, I promise. We want the molecular formula. Remember, the empirical formula is the smallest whole number ratio. It's kind of like an ionic formula, or ionic compound, I guess. The molecular formula will either be the smallest whole number ratio or it'll be some multiple of that, okay? So how do we figure out what to multiply it by, if anything? What information do we have here? We have a molecular weight, okay? So our molecular weight equals 88 grams per mole, okay? How is that useful to us? Can we figure out how many grams are in that? So for CO2 equals how many grams per mole? You guys remember we just did this? It was 44. If you add them up, 12, 32. So you might be able to see this mentally, but just in case you don't, the process you're going to do is you're going to take your molecular weight, you're going to divide it by your empirical formula weight, and then you get a number. What's this number you get? 2. And that will probably be a whole number as well that you're going to multiply it by. Okay? So you get this number, and then what are we going to do with it? We're going to apply it to our formula. So our final formula, our molecular formula, is C2O4. And I think we just did a science. Do we feel good about this? We feel marginally okay about this? Do we have feelings about this? All right. We're moving on. That is empirical formula and molecular formula. Odds are you won't get a combo question. I'm not guaranteeing this, but if I were writing an exam, I would do like one about empirical formula and then I would do one about molecular formula. So probably have them be separate. But this was a combo. That's fun. Okay, now we're going to look at octane. It's how you're going to speed out of here after you finish your finals, and your mom's going to feed you a bunch of food and say how much she misses you. It's going to burn via this reaction. Okay, so we're going to answer some questions about it. What do we do anytime we get a chemical reaction? We are going to balance it. So let's do that, okay? So we have C8, H18, okay? And then O2 yields CO2 plus H2O. Now this particular one is a little bit of a bugger to try and balance, but I gave us this one specifically for that reason. Because if you can balance this, you are a balancing machine. You should be able to balance anything, okay? So that's the goal, all right? So we're going to have C, H, and O, because I don't have much space. So we're going to do it on the left, and we're going to do it on the right. C, H, and O. We're going to have running totals of how much we've got, okay? So let's first evaluate our situation. We have 8 carbons. Now keep me on track if I go off the rails here. We have 8 carbons. We have 18 hydrogens. We have 2 oxygens, right? On the left. On the right, we have 1 carbon. We have 1, 2, 3 oxygens. I don't know why I counted them out of order. That's okay. And then I have 2 hydrogens. I'm keeping you on your toes. Everyone good with their setup? Okay. So, typically, if you have something that's got carbon, hydrogen, and oxygen, you want to balance it in that order. My particular rule of thumb is you always want to try and end with whatever's by itself, okay? Because if you do that, it's really nice. It just kind of like cleans up everything that you've done and doesn't mess everything up more, okay? So that's the idea. So we have 8 carbons here. We have 1 carbon here. What do we want to do? We want to change this. We're going to make it 8 carbons, okay? 8 carbons, 8 carbons. You see how I do this? I'm updating my totals. But it also changed something else. What do we change? We changed oxygen. So we have 16 plus 1, 17 oxygens. Don't forget to count every single one. And also, please do not add it to your previous total or try and be like, oh, we had this before, so we definitely have this now, because you're going to do something wrong. So just re-add them up every time. It's going to be your best way to handle this. Okay, so our carbons look okay. Hydrogen, 18. Hydrogen, 2. What do I want to do? 9. But now we've gone and messed up our oxygens yet again. So we had 16 here plus 9. What does that give us? Should give us 25. Okay? And now we get to the oxygens. Do you see the issue? Because there is not a number, a whole number, that you can multiply that oxygen by to get you where you want to be. Okay? Because it's not going to end up being 25, right? So, there's 2 ways to handle this. One is a sort of like when in doubt, double everything methodology. The other one is what I'm going to show you, which will get us to the same place, but I have a different reason for doing it. Okay? So what could we put here for oxygen that would solve all our problems if we were allowed to? What would get us to 25? 12.5, right? So we do 12.5. Because then we'd have 25 over here and we'd be done, right? But we're not allowed to have a 0.5. So what are we going to do instead? Or what are we going to do with this? We're going to multiply everything by 2. So I'm going to just rewrite this down here. So we'll have 2 C8H18 plus 25 O2 makes 16 CO2 plus 18 H2O. And that should be balanced. So the thing that you want to check after you do a big balancing problem is you want to make sure that every number, every coefficient is not divisible by the same number. Because if it is, then that means that you went too far. So if everything here was an even number, you could divide it all by 2. You know what I'm saying? But because one of them's an odd number, that's the smallest whole number ratio. Okay? So, armed with this, now let's do some calculations. Yay! Well, it's okay though, because secretly, like, it seems like this is a really big involved problem, and it kind of is, but you were going through all these different concepts, so I'm actually just kind of sneaking it all in there under the guise of one problem. Okay. Also, I do want to make mentioning, because it is just after 2 o'clock, we do have until 2:30, and I'm going to go as far as we can. If we run out of time at the end, I will post online the remaining solutions for you. Okay? So we'll go as far as we can, but I'll give you the rest if we do not have it, okay? And I'll show you where to get that if we come to that point, okay? So, anyway. Let's keep going until then. I just want you to not panic, all right? We're going quality, not quantity. Although I went for quantity on the review, so, you know, something's going to have to give, and I'm not going to rush through it and have it not make sense. Okay. If your car uses 10 kilograms of octane, 20 kilograms of oxygen, how much carbon dioxide could be released into the environment? So what kind of problem is this? I heard some rumbles, but I hope those rumbles involved, this is a limiting reactant problem, because it is. Because you have two different reactants, and we have to calculate a product. Okay? So we have 10 kilograms of octane. So I'm going to put CaH18. Okay? So first we're going to go to grams. 1,000 grams CaH18. 1 kilogram. Okay? And then now that we are in grams, what do we want to do? Yeah, we got to go to moles, okay? So we're going to say that 1 mole, I'm going to put OCT, and then that'll be our thing, okay? And then we need a number of grams for this, okay? So calculate that for me real quick. 114? Okay, cool, thanks. I thought about doing some mental math, and then I was like, this could go really tragically wrong, so I decided to not. It's amazing how your math skills diminish when you're in front of a couple hundred people. Okay, so now we're in octane, all right? So we want to figure out what? We want to know how much carbon dioxide, right? So do we have a way to convert between octane and carbon dioxide? Yeah, okay. So how many moles of carbon dioxide are we going to have here? What's our number going to be? 16. That's why we did this. Okay, and then how many moles of octane? 2. Okay, and then we are now in moles of carbon dioxide. This is something that we can work with. The question is asking how many grams of carbon dioxide. So actually, why don't we go ahead and take it all the way, and then we'll analyze this at the end. Okay. So how do we get to grams of carbon dioxide? Molar mass, thank you. What's our mass going to be? 44 grams of CO2 per 1 mole CO2. And now we can finally calculate an answer for ourselves. I know this is a big one. $3,800, huh? 30,000. We have lots of grams. That's okay though, because the kilograms would be more realistic. 30,877 grams. No? 814? Okay, it looks like you didn't divide something by 2. Okay, so I think, is our general consensus that we're in the 30,000 one? All right, that's why we're doing the group think here. Make sure that you guys are real careful with your calculations. Grams CO2. Now, this is not how many grams are definitely going to be made. This is how many grams could be made if the octane is our limiting reactant. But we don't know that. We don't know that this is the one that's going to limit our amount of product. So how do we figure out which one? What are we going to do? What's our process? Huh? Well, not quite. So we're still trying to, because we have two different reactants with two different numbers, right? So we have to actually take our other reactant and do all this whole fun escapade one more time. So let us do it. We have 20 kilograms of oxygen. Again, we have O2 now because we're in a real reaction. Okay. 1,000 grams. 1 kilogram. Okay, so kilograms go away. In this case, we have 1 mole, O2. This is going to be 32 grams of O2, not 16. Grams. Okay, how do we get to moles of CO2 from here? We have 16 moles CO2. How many moles of oxygen? Moles. Okay. So now we're in moles CO2. What's our last step? Grams. By the way, do you guys see why it's so useful to write out every single bit of the units? Like, it's tedious, but you have to do it because you have to know what you're dealing with. If you just have moles and moles, it's not going to make any sense. Okay? So, give me a number. Any number, preferably the right number. All right, 17,562. I'll just take it as that. Did everyone else get that? Yeah, I know you guys are still calculating. Huh? You guys got the same? Yeah? All right, we'll take this then. Grams CO2. Okay, so we now have two different calculations, okay? This is basically like saying, you know, if you're dealing with like, let me try and think. If you're dealing with like party supplies, right? Okay, so let's say you're going to have like 10 people over for lunch, okay? And these people really like pizza. We'll talk pizza one more time for our last hurrah here. So if you have 10 people over and they really like pizza, let's say you've got, let's say that you're going to have 10 plates, okay? But you're going to only have 8 pieces of pizza, and they wanted 1 piece person, right? You see how our numbers are going to end up not working out quite perfectly. Anyway, the idea, I'm going to just kind of cut to the chase here. The idea is that if we were only going based on the oxygen, we'd be able to make that much carbon dioxide. If we're going only based on the octane, we'd be able to make that much carbon dioxide, okay? We have to go with our weakest player here. So the one that's going to be valid is the smaller number, which means many things. There's many implications here, okay? So we can say that oxygen is our limiting reactant, which is really interesting, right? Because we had 20 kilograms of oxygen, only 10 kilograms of octane, and yet oxygen was the one that was limiting. So you can't just look at them and say, oh, I know which one, you know? So that's one question that we could answer. And then we have another question. How many grams of which reactant would remain? Okay, this is like the bane of many people's existence, this question. Okay, so what we need to do is we need to figure out how many extra grams of CO2 the octane could have made. And then we're going to trace it back to figure out how many grams of octane are left. Okay? So our first step is to subtract these. Go ahead and do that for me. Give me a number. Okay, so we're going to have 13,277 grams of CO2. Now this is the extra that octane could have made. All right, to be clear, that's what we're working with, okay? So we're going to work this back to how much reactant we have left, but we're going to do the same exact process. It doesn't matter how they word it. If they tell you you've got this and you need to get to that, just find a way. Don't worry about the conceptual implication as long as you know your path. Okay? So we have 1 mole CO2, 44 grams. Okay? And then we need to go to octane from CO2. So we're going to have 2 moles octane, and then 16 moles CO2. Boom, boom. Okay? Now that we are here, we need to get to grams, okay? So we're going to look back. So we had 114 grams of octane per 1 mole octane. So now we have the ability to figure out how many grams are left. How many grams? Yeah? 4299. Everyone get something around that? Something like 4,000? Or 299? No? You got what? 47,299. 4,300? Yeah? Okay. Looks like we got a calculation issue here. All right. Do we have a consensus that that's about what we get? Yeah? Okay. Grams of octane. I don't calculate these ahead of time because something always ends up happening and then I don't give you answer choices that have like the answer. And then that's not good. Okay, but do you guys see how we did this, why we did this, what's happening? You guys see all these things? Okay. Now, believe it or not, we're still not done with this problem. We have one more follow-up. Because, you know, we do. Okay? Our follow-up is if 500 grams of carbon dioxide were actually produced. Now, this is obviously a very, very low yield, but that's okay. We want to know, what is your car's efficiency? What are we asking then? If we ask for the efficiency, what is that saying? We want percent yield. Okay? So how do you do percent yield? It's actual divided by theoretical. What was our actual yield? So it says 500 grams were actually produced. 500 grams were actually produced. Okay? Now, what is our theoretical yield? Our theoretical yield is that guy. Now, this is what I get for making questions without like calculating them through first. We end up getting kind of weird numbers, but that's okay, because the concept is still steady. We have 17,562 grams CO2, and then we have a pretty clunker of a car, but what is the decimal that we get? Well, yeah, I was just gonna, yeah, if you want to go ahead and multiply by 100, give me the percentage. 2.83? So that's what we would get for our percent yield. An actual, more realistic percent yield for a car would be about 40, which is still not necessarily what you would want. That means that 60% of the gas you buy is just thrown away. Basically. I mean, it's, you know, the whole car mileage thing, they account for all that, but like, it still kind of makes you sad, you know, because it's like, man, we could have gone 60% farther on that same amount of gas. Like, what a bummer. But that's okay. So, we go with this one. That is like the core of all the stoichiometry stuff. And now we're gonna just keep going until we run out. Okay, we want the molarity of a solution made from 25 grams of magnesium chloride and 800 milliliters of water. How do I calculate molarity? Moles per liter. Okay, so I have 25 grams. Do I have the ability to get moles? Yeah. Grams of MgCl2. Remember we did the formula for that one earlier? And that's the kind of thing you need to be able to know the formula for your ionic compounds, because now we have to find a molecular weight for it, or rather a formula weight or whatever. But same thing. 1 mole MgCl2. What's my weight here? When you add them on the periodic table? 95, something like that, 95.2, okay. Okay, and then what's our answer? Or how many moles do we end up with? Huh? 0.263. Thank you. Okay, so we have a mole amount. Do we have the ability to get a liter amount? Yeah? How? Yeah, so we're just going to move this guy over, 0.8 liters. You can also multiply it by, you know, the conversion factor, but we're going to just do a little quick mental math here. So give me a molarity. Huh? What was that? 0.328? Anyone else get 0.328? You guys got 0.328? Excellent. Now that capital M, you call the unit molar, which is weird, but that's okay. All right, we feel okay about this? Moles, liters. You can use it as a conversion factor. Tends to be fun. Okay, so this is a dilution question. Okay? Now, everyone gets all hung up on the difference between dilution and titration. There's a very big difference. Dilution means that you have like some kind of, you have like lemonade concentrate or whatever, and you water it down, right? So you're just thinning it out, you're making it less strong, okay? A titration is when you are combining an acid and a base until they neutralize. So we're dealing with something very, very different here. Dilution, there's no chemical reaction, okay? Do we have an equation for how dilutions work? Do you guys remember? So M1V1 equals M2V2. Okay? So we have our M1 is 500 milliliters. So, sorry, that's not true. That's our V1. Hold on. Our M1 is 2 molar. Our V1 is this 500 milliliters. The interesting thing with dilutions is it doesn't have to be in liters like molarity does. You just have to have them in the same unit. Do you guys rather do milliliters or liters? Yeah? Let's try milliliters. Let's just see what happens. We'll just go crazy. We'll do craziness. All right. We'll go milliliters. We'll do 500 milliliters. But you should try it as liters and make sure you get the same answer. And you probably will. Okay? So we want to know new molarity. So M2 is our question. And then V2 is going to be 2,000 milliliters. Right. So 2 times 500 equals 2,000 times some variable. All right, so we get X is, I'm going to do my mental math here, so watch me now. 1,000, 2,000, 0.5. Now, if you had done this the other way, you would have just done 0.5 and then 2. So, not a whole lot of difference there. It's just whatever you prefer. But just make sure that they're in the same unit. If me saying this confuses you, then just always do liters for everything, and then you won't get it wrong. So there's that as well. Okay? So that's a dilution, very straightforward. Unfortunately, a titration is different, okay? Now we have the reaction between sulfuric acid and sodium hydroxide. Okay? So we're going to need to write an equation, we're going to need to balance it, and we're going to need to do some calculations, okay? We haven't yet talked about how you put together acids and bases. So sulfuric acid, it's going to be H+, and then ic goes with 8. Remember that? Ic 8. So we're going to do sulfate. Do you guys remember what sulfate is? SO, can you see this? Okay. SO4 2 minus. So what does this look like when we put it together? H2SO4. And then we have sodium hydroxide, Na+, and then what is hydroxide? OH minus, so it's NaOH. Okay, so let's write this all out. We have H2SO4 plus NaOH yields, what do we get when we titrate a strong acid and a strong base? We always get water and a salt, right? So we're going to combine the Na with the SO4. So it'll be Na2SO4 to balance it, right? I'm skipping steps. Hopefully you're with me. Barely? Well, hang on. We got this. I want to just make sure that we can get through this problem because we're pretty short on time, but we're going to try and finish this one, okay? All right, so let's balance real quick, okay? So it looks like sodium, we have 2 here. We only have 1 here, so I'm going to put a 2 there. And then my sulfurs are good. My oxygens, I've got 4, 5, 4, 5. My hydrogens, I have 2, 3. I have 6 oxygens? Okay, yeah, you're right. Sorry. My math is, that's why I need your help. And that's why you shouldn't probably rush it like this. Okay? 4 and then 6. Okay? And then we have 5 oxygens here. Okay? We also only have 2 hydrogens here, and then we have 3 hydrogens here. So let's go ahead and slap a 2 on this guy. Okay? So now we've got, and I added up my hydrogens wrong too. So we have 2, 4 hydrogens, and then we have 4 plus 2, we have 6 oxygens, and then we have 2 plus 4, 6 oxygens. I think we're balanced. Do we look good? I'm sorry if I totally blew you away with that, but please check it later, okay? So what we are going to do is we are going to take, it says what quantity of a 3 molar solution, okay? So we're looking for a volume, okay? What quantity of this is required to completely neutralize 500 milliliters of a 5 molar sulfuric acid solution? We're going to start with the other one, okay? We're going to start with this one. So we're going to have, I'm cutting steps here, 0.5 liters of H2SO4. Okay? And then we have this 5 molar. That means that there are 5 moles of H2SO4 per 1 liter H2SO4. Liters are gone. Now we're in moles. So we're trying to get to sodium hydroxide, right? Sodium hydroxide, we're going to have 2 moles NaOH for every 1 mole of H2SO4. Okay, so now we're in moles of NaOH. We're going to calculate for that, and then, well, actually, we can probably take it all the way, right? Can't we? Because we have a 3 molar solution of the sodium hydroxide, so we can actually take it that one step further. All right? If it's 3 molar, that means that in 1 liter of NaOH, we have 3 moles NaOH. And then we should end up in a volume. Can someone do that? $1.67? Okay, so we get here 1.67 liters of NaOH. And that's our answer. So from here, if you will give me your ear for a moment, we are out of time, but I just want to say a couple things real quick. Hold on. So for one, please, if you have the opportunity, scan one of the QR codes. There's one up here, and I think there's usually some on the outside of the doors to fill out the survey for this. I will be posting online the remaining answers. You're going to look up SARC, Google site, and this is Chem 1A with Jessica. Okay? So you'll be able to find the remaining answers there. Thank you so much for coming. I really appreciate having you guys here. This has been a really awesome semester if you guys have been hanging out with me. Good luck, the rest of chemistry and everything else you do.